So the other question is who reproduces research, and I think this is, I don't know how, I'm not in this area of kind of genomics and computational biology. I don't know how much this is an issue, but it's a big issue for me. So in order for reproducibility to be effective in any way, someone has to do something, right? So if I just say I publish this paper and it's reproducible, that doesn't necessarily mean anything until you get your hands on, or someone gets their hands on the data and the code and looks at it and does something and maybe even reproduces it, right? So someone has to do something. You have to rerun the analysis, check the code, whatever, try some alternative approaches. So I think, and this is kind of, in my sense, is kind of the analog of replication. It's kind of inherited from that tradition. But the question of who is something and what is their goal, who is this someone and what are their goals is very important, I think. And the way I kind of characterize it is that there's kind of three different types of people who may want to reproduce your research. So if you're the original investigator over here, you say that the truth is A. There's one group, the general public, which doesn't care. So that's the largest group of people. Then there's what I call scientists, who either agree with you, maybe that they agree that they think the truth is A. They may think the truth is B. Okay, so that's fine. Everyone's got a hypothesis about how the world works. And then there's this group of people over here, which believes that the truth is just whatever the opposite. It's not whatever you're saying. And I've sized the boxes. It's proportional to kind of the likelihood that the people in that box will reproduce your work. Scientists, I think, are likely to reproduce it, but they're kind of busy doing their own thing. So there's an issue here, which is that this, in my opinion, is not really science. They don't have a specific idea of how the world works. They just want to know that it's different from whatever you're saying. And so they're very interested in reproducing my work. I've had it, and thankfully, my work's mostly been, almost all of it's been reproducible. So I'm fine with that, but it has the potential to make your personal life miserable. So far my thinking is that, so reproducibility brings transparency, which is critical, I think. And it also increases the transfer of knowledge. There's a lot of discussion about how to get people to share data, which is important. Data sharing is key, obviously, to reproducibility. But I think the key question of can we trust this analysis that we see out there is not fundamentally addressed by reproducibility. And furthermore, reproducibility is this very downstream type of element, and a lot of these secondary types of analyses are colored by the interests and motivations of others. And I spell color with a U because we're in Canada. So that brings us to what I call evidence-based data analysis. And so I think everyone here is familiar with the idea that a true data analysis involves stringing together a whole lot of things. Lots of tools, lots of methods, as this long pipeline of stuff that you have to do any real data analysis. And so a lot of times the methods are standard. Everyone does the same thing for a given piece of the pipeline. Or if there's no standard, then you just kind of make up whatever you want to do, right? So, and the basic idea is, I think, that I want to kind of translate to kind of a lot of biomedical science, is that we should just use thoroughly applied, thoroughly studied methods that we kind of agree upon in our subgroups of the scientific community, that these are the appropriate methods to use. They don't have to be perfect, but we have to kind of, hopefully they're like the 85% solution. And there should be evidence to justify the application of certain methods. And as statisticians, we do this all the time. We compare different methods, either by simulation or theory or whatnot, and we kind of say, well, which method is more appropriate in a given circumstance. So just a very quick example, this is a histogram that I generated in R. I just typed hist x, and of course the histogram is just a smoother, and the most important thing in a smoother is the bandwidth, right? And so I didn't do anything, I just made this histogram. So how did the bandwidth get chosen? So it turns out there was a paper written by Sturgis in 1926, published in JASA. A paper is actually a very generous term, this thing was like this long. But who suggested that the bandwidth should be done according to this formula, basically. Later on, when the kind of kernel smoothing became popular, David Scott wrote a paper in Biometrica, which talked about choosing the bandwidth based on kind of integrated mean squared error type measures. So, anyways, the default bandwidth is just programmed in, and there it is. All right, no one argues for the most part with the. Sometimes you want to make it smaller or bigger, that's fine, but usually the default is pretty good. And there's actually some research behind what that bandwidth should be.